So here we go on Chapter 8, Lesson 1. Today our objective is to identify quadratic functions. So far this year we have dealt with linear functions strictly. We're going to identify the quadratic function and determine whether they have a max or a min, meaning a highest or a lowest point. We're going to graph those quadratic functions and give the domain and range. So back to where we left off there, talking about domain and range. Domain summarizes the x values for our function, and our range is a collection of all the y values, and together making the ordered pairs that describe our graph. So some of our new vocabulary is quadratic function, parabola. We're going to talk about the vertex, a minimum, and a maximum. So you can see from, and we're following right along in your book, the function y equals x squared is shown in the graph below. It's not linear. It does not fall in a straight line. It's called quadratic. Anytime we graph a quadratic function, we can see it emerging in the form of a parabola. These are parabolic functions. It can be written in the form y equals ax squared plus bx plus c, where a, b, and c are real numbers. A cannot equal 0 for obvious reasons. If a was 0, we would not have an x squared term, and we would fall back to a linear form. And so the function y equals x squared can be written as y equals 1x squared plus 0x plus 0, where a is 1, thank you very much, b is 0, and c is 0. And so here we have the basic parent function, y equals x squared. Just like when we dealt with linear functions, our parent linear function was y equals x. In 5.1, we had identified linear functions by finding that a constant change in x corresponded to a constant change in y. The differences between the y values for a constant change in x are called the first differences. So if you look at our table here, we do have constant change in x. We have a change of 1. But when we have a quadratic function, we can see our first differences, 1, 3, 5, and 7. These are not constant changes, and that is what we will see with our quadratic function. Constant change for x. First differences in a quadratic function are different, but if we look at the second differences, we can see that they are then constant. So I want to draw your attention to this. The second difference is in relation to the second power. The same thing would happen if we had a cubic function. We would find the third differences to be the same or constant. Identifying quadratic functions, we're going to tell whether this function is quadratic or not. First of all, we look at the change in the x values. We see that we have a constant change of 1. Since you're given a table of ordered pairs, the x values, see if the second differences of the y value are constant. So we look at our first differences from -9 to -2. We went up by 7, up by 1, up by 1, and then up by 7. We can see a real symmetry here, and later on that will point us in a direction to determine where we might find our vertex. So if we look at the second differences, we see -6, 0, and +6. Therefore, the function is not quadratic. The second differences are not constant. It says make sure that there's a constant change in the x values before you try to find the x or the y values, the second change in the y values. So, just like the table, we can look at a function and see whether it is quadratic or not. Since you're given an equation, we want to use ax squared plus bx plus c for our form of a quadratic function. This function happens to not be quadratic because the value a x squared is 0. There is no x squared term. It says tell whether this function is quadratic. Can we put it in the form ax squared plus bx plus c? If we add 10x squared to both sides, we get the equation y equals 10x squared plus 9. Therefore, we can put it into the form y equals ax squared plus bx plus c. Here's a helpful hint, good for your notes, of which you guys are taking notes, and these are worth 10 points. Just because I'm not here, Mrs. Rourke is, and she's going to be checking. In a quadratic function, only a cannot equal 0. It's okay for the values b and c to equal 0. So this is your first check it out on example 1. It says tell whether the function is quadratic, and then explain your reasoning. Well, if they give us a list of ordered pairs, we can put that into table form, and we can check our x values and how much they are changing by. We see a constant rate of change for x. We can also see the first differences in the y values. They are not constant, and we don't want them to be if we're looking for a quadratic function. So when we check the second degree differences, we see that we have a constant change, and therefore we can say that this function is quadratic. Tell whether this function is quadratic. Well, we know that we have a common form, y equals ax squared plus bx plus c. If we can put it into that form, they say by subtracting x from both sides, we can write it in the standard form, and we know that c, because we don't have a constant on the end, is equal to 0. We can look at the graph of a quadratic function. It's called a parabola, and it is curved, never linear. To graph the quadratic function, we can generate ordered pairs to see the shape of the parabola, and then connect the points with a smooth curve. We're going to use a table of values to graph this function y equals 1/3 x squared. Making our table, we let x take on any values we want because it is independent, and we're going to fill in the y values. So what we've done is taken -2 powers first, we've squared that for a positive 4. 4 times 1/3, 4/3. We've gone on and completed the table. Then we're going to graph the points. We can see that our points definitely form a slight curve in parabolic fashion. So we can say that we have a quadratic function. We knew that from comparing it to our standard form of the function. Now let's take a table and graph y equals -4x squared. Making a table of values, we usually like to do a couple negatives surrounded by 0 and a couple positives. We'll be able to draw more conclusions later about this form of the quadratic equation. Not having a bx and c, we know that this hovers right around the origin. So we're going to plug in our values -2, -1, 0, 1, and 2. Plugging those in, graphing the points, and we can see this time that we have a parabola opening downward, and we might be able to draw some conclusion right here from the form of our equation. We can see that we have a negative leading coefficient, and that is every time going to give us parabola opening down. You guys are going to do check it out example 2a. Use a table of values to graph each quadratic equation. Please stop the recording right here, finish your table, and create your graph, and then compare it. So you've had some time to create your table. From examples, you could have chosen these, you could have chosen other ones. Graphing the points, we come up with a parabola that sits 2 units above the origin, and we might be able to assume that +2 at the end of our function, our constant value c, has something to do with that translation of our parabola 2 units up. Check it out 2b. Please create a table. Turn off the recording, create your table and your graph, and compare it to the solution of y equals -3x squared plus 1. Remember, these are your notes. This is what you'll be graded on when I get back. Your 10 points for each lesson that we do. This is lesson 8.1, so you'll have lesson 8.1 notes, and I want to see all these check it out problems in there. So go ahead and turn this off, complete 2b, and then come back and check. So after looking at examples 2a and 2b, some parabolas are open upward, some are opening downward. Notice the only difference between the two equations is the value of a. The leading coefficient in our standard form y equals ax squared plus bx plus c. This value a, whether it's positive or negative, determines the direction of our parabola and how it opens. A parabola opens up when a is positive, greater than 0, and it opens downward when a is less than 0. So we're going to identify the direction of the parabola just by looking at the function. It says tell whether the graph of this quadratic function opens upward or downward, and explain your reasoning. Well, we're going to take a look at this. I see a negative 1/3 in front of x squared. However, we don't have it in standard form yet. It must be in standard form in order to use that leading coefficient to determine up or down. So we're going to solve for y by adding 1/3 x squared to both sides of the equation. We can then see that a is positive, and from the notes that you just took, you now know that this parabola opens upward. Identifying the value of a is 1/3, a is greater than 0, it opens up. Let's take a look at this example 3b. Tell whether this graph opens up or down. Again, we don't have it in standard form. We've got to put it in standard form. Ax squared plus bx plus c. I see when we do that, the sign in front of our leading coefficient stays with it. That minus 3x squared indicates a negative, a sign of negative. So we're going to take that with it. The value of a then is negative 3. And since a is less than 0, in this case, our parabola would open downward. You guys do check it out, 3a, tell whether the graph opens up or down, and explain your reasoning. Please turn off your computer, pause the recording, and come back for the solution. So we take a look at our function f of x equals negative 4x squared minus x plus 1. And we can see our value a in front of x squared is negative 4. A is negative, therefore less than 0, and the parabola opens down. Let's do the same thing with 3b. Take a look at the function. Turn the recording off or pause it, and then decide whether it opens up or down, and explain your thinking. Well, we can see that if we put this function in standard form, adding 5x squared to both sides yields this function, y equals 5x squared plus 2x minus 6. The value of a is 5. Since a is positive, the parabola opens upward. So as we just discussed, we have parabolas opening up or down, and you guys can think to yourselves the images of those parabola. If a parabola opens up, then we know that it has a low point. It has a very low point, and it will get no lower at any point in the function. If the parabola opens up, the vertex is the lowest point. If it opens downward, now we have a highest point. So here's something for your notes. It says, if a, our leading coefficient, is greater than 0, our parabola opens upward. The y value of the vertex is our minimum value. So you can see in this graph right here, it opens up, a is positive, therefore we have a minimum. Likewise, if a is less than 0, parabola opens downward, we have what we refer to as a maximum. When I plug in this x value 3 into the equation and evaluate, I get y equaling 5. Our maximum value is 5, whereas our minimum value over here, when we plugged in the x value negative 3, we got a y value of 0. Therefore, our minimum is 0. Over here, our maximum is 5.